2016. We have advanced since then. And early in 2017, with colleagues from Germany, we demonstrated something else, that you can actually snatch a secret key with these random corruptions, even if the memory is encrypted. And we're going to see even more problems today. So I'll give some background, starting with old news. So we all know that if you have an adversary that has access to a platform, it is a big concern. And this concerns mobile devices that can be stolen or lost, and up to cloud computing when you are running some workload over an untrusted environment. Now, the fact that reading and writing the memory, so that these capabilities can lead to an attack, these things have been demonstrated with different physical interfaces, Thunderbolt, PCIe, and other USB standards. So we know that it is possible to read and write the memory, and attacks have been demonstrated, but they have been demonstrated on clear memory. And the advantage from the viewpoint of the attacker of reading and writing clear text memory is that you can change anything to anything. Because if you can read and then write, you can just read something, change, flip all the bits that you wish, overwrite this, and you have changed any plain text to any other plain text. And things have been demonstrated to lead to an attack. But this is easy, right? If the memory is in the clear, then obviously, and you have these tools, obviously you can do some damage. So too easy, right? So we are going to assume throughout this talk that you have a device or a platform where the attacker has the capabilities, the physical capabilities to read and to write the memory. But we are going to make the memory encrypted and see if this is good enough. So, what in general are the strategies of an attacker? So, there is a passive attacker. He can only read, eavesdrop the DRAM, but cannot inject any modification into it. So in reality, this scenario doesn't really exist, because if you have the tools to read the memory, the same tools can be used to write the memory. Now we have an active static attacker, and this can read one time, can read static data, but cannot modify it. So the most known example for this is the cold boot attack, where you have a device, and you rip out the DIMMs from the socket and you freeze them and go rapidly to read. With high probability, you can recover most of the content that was on this DRAM. And if there are some secrets, okay, bad things happen. For example, your disk encryption key, if it is stored in the memory and somebody rips it out and is able to read most of the data, so okay, and now we can get your disk. So this is an attack on the privacy of the data, but it's not repeatable. You cannot just put them back. We've tried, by the way. It didn't work. And now we are more interested in active dynamic attacks. So the adversary, the attacker, is able to read and online modify things as he wishes. And this is a more dangerous situation. So this is the situation we are going to focus on. So how about transparent memory encryption? What I mean in transparent is that there is some encryption going through, that everything that goes to the DRAM is encrypted. Going back, it is decrypted back. And the keys are, of course, internal to this device or this environment. And this is the protection. Now this seems to be a very good solution, right? because it is very simple to implement something like this, or I would not say very simple, but much simpler than implementing something with integrity, because it is basically a filter that takes data going through and just passes this through some process. The same amount of data is going. So if you have a cache line and you move it out to the DRAM, it is the same payload of a cache line. Nothing else is added. Whereas if you want to do some authentication, there needs to be additional payload to put some authentication tags, and this is much, much more complicated. Furthermore, if you want anti-replay, you need to have some internal payload, and this is not only complicated, it is also very expensive. So a very easy solution in this respect, with this comparison, is just to encrypt the memory. You put something, you put some keys, and you suffer the latency. Maybe you can just put a little bit more hardware into this, so this is a matter of cost, but and then the latency would be reduced and the throughput would be very good, but basically it is very cheap, relatively very cheap. So now the effect is that the attacker has limited control on the result of active attacks. So this type of mitigation doesn't change the fact that the adversary is able to read and to write the memory, but now is much more limited, right? Because, okay, everything is blinded. Presumably you cannot break the encryption. So let's go to what we call blinded random block corruption, BRBC. We made up these acronyms. So what can the attacker do? The attacker with these capabilities of reading and writing the memory, what can this attacker do under the assumption that the memory is also encrypted? So first of all, he is blinded. Blinded, it is in the sense that he doesn't know the plain text memory value that he reads on the DRAM, and because they are encrypted. So he's blinded. But he's also blinded even worse, because if he changes something and the mode of operation of this encryption is some block cipher, then any change in a single bit is going to affect randomly the plaintext that would be decrypted from the DRAM after that. So this is why not only is he is blinded, but he has a random block corruption mode. So whatever he touches is going to affect randomly 128 bits. Well, in practice, encryption goes over 128-bit blocks. So, and the corruption would be completely random, but this is the property of block ciphers. So he can make the changes, but he doesn't have any control on the influence that this is going to have when the affected ciphertext is going to be read into some plaintext. Who knows what it is, completely randomized. So the question is, now that the attacker is so limited, has so little control, maybe this is sufficient to have a good enough protection. What do we mean good enough? Well, maybe in practice there isn't anything you can do in order to attack this system. Of course, privacy is protected because everything that goes out to the DRAM and can be read silently is going to be protected. So maybe, hopefully, this is a good way to protect a system without paying a lot of overhead, a lot of cost, and a lot of latency for doing encryption with authentication and with replay. So what do you think is the answer? Is it a good enough mitigation? I think you can guess no, right? Otherwise, I wouldn't be here and giving a talk about memory encryption not being enough. So here is the bad news, right? It's not good enough. So although the capabilities of the adversary are very limited, still you can do a lot of damage. So you can create some time to check and time to use, raise conditions and make some modifications, and this way you can affect the flow of some code. And if you know exactly where and when to hit this piece of code that you want to change its flow, then you can do, as an attacker, a lot of damage. Or from the attacker's viewpoint, it is a great success. So this is what we are going to show, and this would give some bad lesson about the hope that just memory encryption is sufficient. So let's model the attackers. We model them as ABC. Well, it's a nice acronym. So what is ABC? So who is the attacker? The first attacker is A, access-seeking attacker. So he's not the owner of the platform. He has physical access to this platform, and he wishes to get a user access to steal some secrets. You can think of it as somebody is taking your laptop or your phone, and this is now found in a locked situation, so the adversary doesn't have the password. Still, he wants to log in. Now, the second one is the breaching attacker. Now, the breaching attacker is a legitimate user of this platform, but he wishes to breach some of the system policies or to circumvent some restrictions and get more privileges. So now this attacker is much stronger, right? Because he has more control on the system. So the A is the weakest attacker with the least amount of influence on the system, and he wants to log in. The breaching one is stronger, and I will explain what the difference is. And the last one is the strongest attacker, is the conspirator. So this attacker is not only a legitimate user, he's also an administrator of some environment, and he wants to breach the privacy of host VMs. So what is the difference? What is the difference? The A adversary has a one-time shot, because in many cases, if you try to do something and you fail, the system will just hang out forever and you will have to reset it. So you have a limited or one-time or a limited number of attempts until you are lost. The second, the breaching attacker, can try as many times as he wishes, right? It's his own platform. He just wants to get some more power. So if something fails and he needs to reboot the system, okay, so be it. It's just going to take more time, but it's possible. And the worst attacker, who is the conspirator, okay, he's the administrator. He can do anything, right? He just wants to violate the privacy of some hosted VMs. All right. The remaining time. So here we are going to see how to become a root on a locked system with a BRBC attack. And we're going to show this. So what you see here is the actual flow of a login code of Linux. This is what happens in reality. So there are some global variables in the code. There is another global variable. It is called pre-auth flags, the pre-authentication flag. This is just allowing somebody to make a bypass if he has already committed a correct password in order not to bother him again and again with give me your password. And now you have some pre-authentication flag. Remember it, it's going to play some role. And now you have the code. And now the code is doing something. If pre-authentication enabled, there is something that happens. Eventually, you need to go into the login code, into the login. And if you are breaching or overwriting this block, if pre-authenticated flag, then go to authentication OK, then you're going to win. So all you need is to know when to hit and where to hit. But the structure of this code is known. It's part of Linux. You can just go and see. So you know exactly the addresses where all of the variables are stored in memory. In particular, this flag, pre-authentication flag. All right. So if you are able to change pre-authentication flag from nothing, 0 to 1, then it is going to skip the authentication logic. It will not be executed, and then you're in authentication okay, and you've won the game. So now let's see. So we have some race condition, but very fortunately, in this case, the login program itself allows to find exactly where to win the race, because it is built on what is your login, wait for input, then what is your password, and then you get the result, passed or failed. And if you failed, then what happens? Again, what is your login, what is your password, and again and again. So, here is the experiment. Actually, I'm going to show you 2 experiments that were done. One with a debugger. So we just hooked a debugger to a real system and just play with it and did the attack. But then you would say, you're cheating. You cannot run a debugger on a locked system, right? I just stole your phone. How are you going to hook a debugger to my phone, lost phone, where you don't have a login? But this is only a demonstration just to show the race conditions and that this can be done. But then we actually did it with a JTAG interface to a CPU with actual results. So I'm just saying that it is not really, well, first of all, this is a fact of life. That's the login code of Linux. But it is not so easy to do the protection, because to do software-based protection, because bottom line, you need to compare a single bit, right? There is a single bit, either pre-authentication is okay or is not okay. So there isn't much you can really do in the software. But anyway, this is really the software itself. So here is the BRBC, random block, blinded random block corruption on a login program, and this is a debugger based, because this demonstration we can just see what happens. So we have, okay, we are in this situation. We want to be root, right? If we can log in, why not be root on this device? Okay, we need to put some password. Of course, we don't know the password, but we are going to use the debugger and the debugger's capability to override the memory with some garbage, right? Because remember, the model is that the attacker doesn't know sees only ciphertext. So he doesn't know what the plain text is, and he certainly doesn't know how it is going to be decrypted, into what it is going to be decrypted if he changes anything. Because you can say, okay, if you have a debugger, why don't you just read everything and you're done? But the demonstration here is that we can just do this blindly without injecting anything specific. So we have this, we are going to just put a breakpoint into this login, and we type something, right? We want to be root. We just type something as the password, and of course, password incorrect, right? We've done one loop. So give me your password. Oh, what is your login? Root, of course, this is what I want to be. What is your password? Just put something. Okay, your login is incorrect. But now we are in a breakpoint, right? Now the system is going to wait again for some input. And this time, the next time, it is going to check if some pre-authentication is okay, right? Because the situation is that after you've logged in once, the next times you don't want to log in with your password again, right? You've done this once. So after the first failure, now we're in a situation that the code will check if the pre-authentication flag is set. All right. So this is our time to corrupt the memory. So we are going to use the debugger and overwrite the memory with something arbitrary, of course, because the game is that we don't know what's in the ciphertext, or we can see what is in the ciphertext, but we don't know what it is going to be decrypted to. All right. So okay. So we are going to corrupt this memory with the sentence 16 bytes garbage. It's just garbage. This happens to be 16 bytes, right? So just write anything, but okay. So here you can see the 16 bytes garbage, and okay, that's it. We are root in the system. Why? Because it doesn't matter. We just need to flip a single bit successfully. So with a very high probability, this is going to succeed in the first attempt. And if it doesn't succeed in the first attempt, then it's going to succeed in the second, or in a few single attempts, it's going to succeed, because all we need is just to be able to flip a single bit. So here is an attack. Actually, I can just tell you, okay, this is the flow that you can see. Basically, we know exactly where in memory we want to hit the pre-authentication flag, and we know when, because we know the flow. And the flow is that we first deliberately try something and fail. Of course, we fail. But in the second time, the system is going to check if the pre-authentication flag is set, and then we just hit the memory, and hopefully, with high probability, we are going to succeed, and we are getting into root. So, if you have a device or a system that is in a locked position, and you want to log in, then if, as an attacker, you have the capabilities to read and to write, in this case, we just need to write. If you can just write something on the memory, then the fact that the memory is encrypted is not going to help too much. All right, so I'm going to do this fast. We repeated this attack physically with a JTAG device. So it's the same attack, the same thing, just we tried it physically, and of course it works. It's a fact of life. We don't really need a device that is really having encrypted memory. All we need to show is we can write 16 bytes of garbage, literally in our case, and it's going to flip the bit and allow you to log in. So first lesson, don't let your phone be stolen. Huh? That's one lesson. All right. So what can we do? The first thing you would say, don't let an attacker have the capabilities of reading and writing the memory. But this is not so easy, because debug capabilities and physical access to memory are there for good purposes. You cannot just disable them and say, okay, I just want... So you can just not have protection take over usability, right? So it's a big problem. What really should be done is to have memory encrypted with authentication, and with a good enough authentication that would frustrate the attacker. He's going to need so many attempts until probable success that it's not going to be feasible in reality. So I'm just giving some flow of what possibly can be done. So memory encryption with authentication, and there are systems like this already in existence, the SGX technology. So today you can buy a laptop with this technology already installed, and this means that some parts of the memory are encrypted and authenticated and also replay protected, right? Because the next thing would be to replay a good password line. So, but this is very expensive, and also it is just, at least currently, it just operates on a small, relatively small segment of the memory. So the problem is still there. There are some VTD, some kind of protections in virtualization, and self-protection over the code is also some kind of mitigation, but it is very difficult, because no matter what you do, you cannot really protect, the software itself cannot really protect itself when it is running. So, okay, the next thing, the revenge of the fault attacks. So fault attacks have been demonstrated on the smart cards world. And they've been used to crack many smart cards, and then there were mitigations and more rounds. And I'm going to show, this is work with colleagues from Germany. I'm going to show actually that you can port the fault attacks from the smart card world into the PC world. And we really did this with the same idea. So basically, we just simulated a memory encrypted system. So the kernel itself was encrypted. We modified the kernel, the Linux kernel, so that it encrypts everything that goes to the memory. Of course, at the cost of degradation in performance, but the idea here is to demonstrate an attack, not to really build a system with this. So it's not really an efficient system, but and then we were monitoring with a process. We were monitoring some victim process, and this process actually was doing RSA with the Chinese remainder theorem. So this is well known. This has been one of the first attacks that were used for fault attacks, and it so happens that if you are doing RSA decryption or RSA signature with a private key, you want to save on performance. Saving goes through using the Chinese remainder theorem, which means that instead of one large exponentiation, which is expensive, you are doing basically two smaller exponents. And this cuts the performance by 75%. So you get a speed up of 4x. Nobody wants to give away such a speed up, so everyone is using the Chinese remainder theorem, but it so happens that if you are playing with the two secret primes and you are making a mistake in one of the exponents, then it is going to reveal the primes that their product is the public key, and you know the public key. So this is the basic attack, and now we were really doing this on a real system with simulated encrypted memory, and on a real code. So the real code was GNU PG that everyone uses. Luckily, it was an old version. So the new version of the GNU PC is already checking. So, okay, what do you need to do when you are doing a signature, an RSA signature? Before you release the signature, you need to check it. How do you check it? You just verify that this signature is really authenticated with your public key. And then if somebody played this trick, it's the signature verification is going to fail, and you know not to release this. So it's called check before release method, but this code, this version of GNU PG 1.6, or I don't remember exactly, did not do this check. The next version already did this. So luckily, this software is already mitigated, but if you're using the old software, it is not. So basically, again, you need, here there was some more work to be done, prime and probe techniques to know where exactly this data structure resides and where the temporary signatures are going to be stored. But again, you just randomly hit something, right? It means that you change the memory, and it is going to, when it is going to be read, it's going to just randomly corrupt a block. And if you randomly corrupt a block, then the half of the signature with one of the primes in this Chinese remainder theorem signature is going to be wrong, and then it is released, and with this you can just do the analysis and factorize the modulus, and from that point on you can just sign instead of this user, whoever this user is. You can send emails. This was an email client, so you can just send signed emails with his public key. A very bad situation, I would say. All right, so now let's go further. What happens in the cloud scenario? So here we have a hypervisor that manages many VMs. Of course, the VMs, each VM can have the protection of encrypted memory. And I'm talking about the latest of the latest idea of memory protection. It doesn't exist, but it has been already published as a technology to come out. So every guest machine could be debugged by the administrator who owns the hypervisor, but it is possible, and this is the new technology that is presumably coming out, it is possible to make the memory of each VM be encrypted with a different key. The key depends on the address, on the physical address that you access from. So now we are in a funny situation from the viewpoint of the hypervisor. Today, the hypervisor can just go to the memory of any VM and just suck in whatever is there, can read all the secrets. Now, if the memory is encrypted, then each VM, including the hypervisor itself, each one has a different key, then the VM can still do the same thing, can access the memory, but now some plain text that was encrypted with the key of the guest VM is going to be decrypted with a different key of the hypervisor. And this is equivalent to the random block corruption situation, because if you decrypt ciphertext with the wrong key, you're going to get garbage. So this is the situation. The hypervisors today have the capabilities of reading and writing, and the naive idea, I would say, was that if you allow each VM to be encrypted with a separate key, you are going to protect the privacy of the VM. Well, the privacy against a passive attacker, yes. But if you have an active attacker like the hypervisor, and this is the attacker in this situation, then the answer is no. So these are real. I'm going to show, actually, so, okay. We have the situation. Each VM has its memory encrypted with a different key, including the hypervisor itself. So the trick of reading is not going to help very much. So we say your data is safe, the VM memory is encrypted, a unique key. So in that case, let's get a root login into your VM. Of course, right? So the privacy is protected from one end, but I'm going to show you that we can just log in as a root. You already know how this is going to work, right? And if the hypervisor can get into a VM as a root, this hypervisor can read anything. It just bypassed the whole protection that the encryption offers. So is it possible? Yes. So did you know? Did you know that you have a config file that controls whether or not the VM is debuggable? And guess who controls this config file? The hypervisor. So you can just go, this is a zoom, as a hypervisor, owner of a hypervisor, you can just set true into the debug capabilities of your VM. And of course, the VM itself, the guest VM, is completely blinded to this. The VM doesn't know if it is being debugged. All right, so this is a very important situation, a very important feature for VMware, but actually in most hypervisors. But, of course, this is going to allow us to do our tricks, right? So here it is. This is the flow. In the end, I'm going to show a video that actually shows this. So, but now you are being trained, so you could follow, and you will see the snapshots of these things. So, first of all, the hypervisor connects to the debug stub of the guest VM. Why does the guest VM allow some hypervisor to debug it? Because this is the configuration file. And who set the configuration file? You know, the hypervisor. All right, so here we know exactly which remote VM to connect to. And now, actually, through the debug, the hypervisor controls the flow of the execution of whatever is running in this VM, and can inject breakpoints, right? So first of all, you can stop the execution anywhere you want with a debugger, right? This is the way to use debuggers. This is why we have debuggers. We want to debug problems. Maybe there are some problems we want to fix. But here, we just stop anywhere we want from the hypervisor. And, all right, the login program that I talked about in Linux is running silently on this VM. Although the user is not going, typically is not going to log in through this login process. Usually he would log in through an SSH interface or whatever, but this code is running silently. Nobody is using it, except us. We are going to use it. So it exists. Okay, you can invoke this program, enter your passphrase. So now the legitimate user looks at his own screen. He doesn't see anything. He is completely oblivious to the fact that he is being debugged and this login is stopped and continued. So he continues working as usual. Enter your password and, okay, as usual, we want to be root, wishful thinking, and we put some password and of course it fails. Now what's going to happen the next time? After it fails, okay, give me the login again, but now it's going to bypass something. Maybe I'm already pre-authenticated, right? So, okay, we stop the execution, but we know exactly when to stop the execution. Right after the second time that we fail, the second time that we are being asked for a login, this is the time for the debugger to stop the execution. And now we go, and with the debugger, we corrupt some piece of memory, a block, at least a block, but we don't care, maybe more. How do we know where? All right. Of course we know where, because the layout of the code is known. The code is known. We know exactly where. Okay, there needs to be some kind of some more work actually to know the beginning, where the code starts from, to know the offset. But we just guess where the start is, and then we know the offset. So we have this breakpoint. We just go and do what we want to do on the memory. You know what we want to do on the memory. And okay, well, I just said this. And this time the joke is we just enter the digits of pi. So here they are. So just for the enjoyment, these are the real digits of pi. We just put them, right? Who cares? All we need is to have high success probability to flip one bit. Okay, so we can put pi. In one demonstration that I gave, it was my birthday. So we put the birthday. It always works. If not in the first time, then in the second time. We don't care. We can just repeat this again and again. And of course we won. We are root on this device. So you have a VM with encrypted memory. Each VM has its own encryption key. And yet, the hypervisor can log in as root, and all of this protection is gone just because of trusting encryption without authentication, right? You can imagine that if we added authentication tags to the encryption, then this trick would not work, because pi and my birthday and 16 bytes of garbage will not pass the authentication. Right, but authentication is very expensive and very slow. So you see the dilemma. We won. So the video, you will see it. Oh, I'll show the two videos in the end. So let's just skip. Now you probably are saying to yourself, okay, you are repeating the same trick again and again. You are flipping one bit. So if we only were able to solve the problem of one bit, we will protect it somehow, then you are done. So this attack is not going to work. 10 minutes, yes. I'll finish in 10 minutes. Now I'll sweep through, I'll tell you again. So we have another demonstration. We call it beyond the single bit conditional, right? So it's not a single trick. Okay, let me just tell you, we did the same thing, but But now you can do something. Okay, I'll skip just to the Linux. Okay, so here it is. The Linux kernel, this is part of the stack, has many variables. So what we are looking is for a short variable. A short variable means 32 bits. So is there something here which is defined as an integer? Let's look. Oh yes, there is something. The effective UID, right? So if I want to attack a process and I can change the ID, the effective ID of the process to be 0, then this process becomes root, right? So I'm going to attack my own process with this debug capability or with whatever capability that allows me to overwrite the memory. And if I know where, and I'm patient enough to do it up to 2 to the 32 times, then on average, I can just switch my own executing code to a root and just elevate my privileges. Is it possible to do something like this 2 to the 32 times? Yes, you will see. It doesn't even take a lot of time to do 2 to the 32 attempts. Maybe 10 minutes, 15 minutes, and you are there. So I just have to, just to skip. Okay, this is just, okay, there are several possibilities for the layout, the memory layout of these variables in memory. And we don't have control, but we can just guess, because the problem is the following: that we can hit a 128-bit region of memory, and these variables are now stacked in each block. They are stacked as 4 32-bit values. So there are several layouts. You need to know where exactly this UID, the effective process ID, is residing, but you can find this, and I'll go to the summary, and then we will see a nice video of the two attacks, and we'll be happy. I don't know who is going to be happy, but so I'll just give summary and conclusions, and then we'll enjoy a film. So first of all, we just laid out a hierarchy of attackers. There are different attackers. They have different desires or different attack goals, and they can be ordered in the level of control that they have. So the lowest one is the A attacker that doesn't have anything except for the login interface. The second one owns the machine and wants to escalate privileges, and the most controlling one is a hypervisor that wants to just hit some other VM. So we saw that in all of these cases, just memory encryption is not enough if the adversary has the capabilities to read and write. So even in our attacks, we don't even need to read, we just need to write, to overwrite something in the memory, and it would translate to random corruption. But we have to assume reading capabilities, because if the attacker doesn't have reading capabilities, then we don't need to protect with encryption. So I'm saying read and write, but for the attack, we're only using write capabilities. So this is the dilemma. It is very expensive. It's going to slow the system to add real mitigations with replay protection and authentication. But on the other hand, unless we are sure that we can disable the capabilities, protect the system from writing something on the memory, then memory encryption is not giving robust protection. So with this, I will finish. I thank you for your attention, but we'll now switch, I hope, in the background, that we will switch to 2 short videos. And so just wait. You'll see the video. The video is actually a video of the actual attacks. The first one is going to be the login attack. And here you have, the subtitles. So, okay, let's look at this. If you remember the attack, we want to get root. So you can see the host, the attack, the victim, and the attacker. You have this, yes. Yes, let's have debug capabilities. We can do this, right, as a hypervisor. All right, you've seen this. So you see the victim and the attacking, all right? So now we are going to debug the other VM. Yes, continuing. Yes, welcome. Right. So this is the Linux login. The user of the VM doesn't see all this, right? All right. What is your code? Of course, when you put something, you're going to fail. Oh, sorry, you failed. So let's do it again, huh? The next time, are you pre-authenticated? So nothing, the VM doesn't see anything, right? All right, and now we'll do this random corruption. So we go to the breakpoint, now we stop, now we are going to run. All right, root, let's be root. What password are we going to do? What? It's incorrect. Let's do it again. We have the breakpoint. It's going to succeed, right? It's a video. I was trying this in a real demo too, but it was all right. Okay. You see the password 1, 2, 3, 4, whatever. It doesn't matter. Yes, and here we are root on this machine. So we can do this again and again and play with whatever. It just, yes, this is pi, right? 3.14, you just put anything you want and you'll become root. It's nice to be root on somebody else's machine. All right. So this is the first video. And now, if the gentleman behind, yeah, all right, yes. So now we are doing this. You see this process ID, right? Attack, and you will see that we are trying many. Current ID is 1001, whatever. We want to make it 0, right? 0 is the ID of the root. All right, so attack in progress. This is the current ID, and you will see minus. Why do you see minus? Because this is some random garbage, and this is an integer, and it is being interpreted as a negative value because we don't control whatever it is. The whole thing is going to take 15 minutes, but I spared you the 15 minutes. We're just going to see this in increments, and you'll see that there are many attempts. Some of them are positive, some of them are negative. It is just the reflection of garbage written into this memory. And I hope it would succeed. I don't know. What do you think? Let's be hopeful. Who knows? But this video is deterministic. Okay, it's okay. But if you are just patient enough, you try again and again, and it doesn't take too long. Maybe we can sing a song. Meanwhile, this is in increments of 10 seconds. The printouts. So what we want to see is eventually a full 0 process ID. And this means that we've become root. So let's see. We can stretch. It should happen. It takes time, right? It's not flipping a single bit, which is easy. But I just want to demonstrate that you can do this. You would not be able to do this on a 64-bit integer. But these variables, this is real. That's the Linux kernel. Fantastic. Here is the ID. I don't know what. So the ID is 0, and yes, we are root. right? So, this is the end of the presentation. I thank you for listening, and if you see next coming technologies that encrypt the memory with different keys for each IV, and this is really a coming technology, then know that something needs to be done about the writing and reading capabilities of an attacker, and this could be the debug or whatever. Something has to be done, otherwise, yeah. All right, so thank you very much.